thank you for joining us today for this public launch of Mushi, the floating mycelium wetland. This is a collaboration with Open Waterfront through Open House Melbourne and ultimately the Melbourne. So thank you. Can maybe move to the next slide. Great, yeah. So thank you all for joining. We're quite excited about this launch and the future of this prototype. It's been a collaboration between Swinburne University, Arup, Studio Edwards, and the Royal Botanic Gardens. And this presentation will walk you through the concept to prototype and the journey of what is known as Mushi. Before we go any further, I would like to acknowledge the traditional custodians of the land in which we are all meeting today. Firstly, I would like to acknowledge the Warrawong and Boonwurrung peoples of the Kulin Nation as the land on which the Mushi prototype is on, and that many on this call will be on as well. I would like to recognise their continuing connection to country for over 2,000 generations. Personally, I would like to also acknowledge the Arunde people of which land I am on today. I wish to pay our respects to all elders past, present and emerging. So this session today, it is a bit of a weird format where in this online sphere, we can't really see you, but you can see us. So that's the nature of these online presentations, and we really encourage everyone on the call today to engage with the Q&A function. There's a chat room. You'll see a little speech bubble above whereby you can post questions, and through the discussion we can answer them via text. But there'll also be an opportunity at the end to have a bit more of a discussion with the team, and we can facilitate those questions going to individual team members. So I really encourage everyone to use it as they see fit. Thanks. Next slide. So what are we all here for? What are we going to talk about? So we'll briefly introduce the speakers that will be running you through the journey. We'll then touch on kind of what this launch was that happened a couple of weeks ago. Then we've got a bit of discussion around what fungi is and how that relates, and then how we designed or how this prototype became designed. What are some of the technical aspects of that? What we developed for the prototype, and what we see as the real next steps and the exciting avenue, which is this biomaterial made from mycelium. So just next slide. So I'd like to introduce our speakers today. We've got myself. My name is Alex Riley. I'm an engineer at Arup. We also have Dr. Tom May, who is the mycologist at the Royal Botanic Gardens, Victoria. We have Nancy Becker, who's the co-director of Studio Edwards. We have Kanhui Chen, who is from Swinburne University as an architectural lecturer, albeit from video. He wasn't able to make it today. And we have Daniel Prochowski from Swinburne University also, who will provide more details around their prototype. So before we kind of launch into some more of the details, I want to just kind of set the scene a little bit more with kind of the overarching themes of some of this work. Plastic in our waterways is one of the greatest challenges of the modern world. Repairing the damage that has been created will take some consolidation across multiple sectors. I don't think I need to spend much time on the impacts of plastic in waterways. I feel like there's a good understanding of that, and hopefully through the rest of the discussion we'll be able to flesh that out further. Go to the next slide quickly. And then on another hand, we see cities, right? a city is a place of, vibrancy, of culture, activity and business, and that, is the real core of our lifestyles. But then also in this image, we see a lot of glass, concrete, steel and plastic. Most of these materials that we're looking at are single use. That is, they are made, they serve their purpose, and they're ultimately disposed. This mentality of linear material use is changing in a way, but there are still a lot of issues that require deeper thought in how we approach sustainable building materials. And finally, I want to touch on just quickly about healthy waterways. Living in an urban context, our relationship with waterways and our lifestyle is somewhat disconnected. What you see on the screen here is an image of the effects of a large storm event, which caused a lot of runoff from the urban context, spilling chemicals into waterways, which resulted in these beaches being closed for a number of days and weeks. This was in Melbourne in 2011, and it really highlights the impact of our role as individuals have on waterways and their development. So if you go to so now we're going to just spend a bit of time and show you what the launch was that we went through at the Royal Botanic Gardens. We thought we would start with the end, and then we'll slowly get to how we got to that point. So I want to go to the next bit. This will go for a couple of minutes. Alrighty, cool. So there it is. That was the launch, and we're really looking forward to now showing you how we kind of got to that point. But before we get more stuck into kind of Mushi as a concept, I'm really happy to pass on to now Dr. Tom May, who's going to tell his perception, or give you a bit of insight into fungi, what they are and what they do. So yeah, thanks Tom.
Thank you, Alex. So I'm just going to talk rather than use slides, and I'm going to give you a quick rundown of what I call Mycology 101, and then talk about what has that got to do with materials construction, and then a little bit at the end about the kind of mycology research we do here at RBG Victoria. So perhaps if you switch to just the live view, because I'm going to do some show and tell. Thanks. Fungi are really different. They're a separate kingdom of the living world. They're not plants, they're not animals. They're actually more closely related to animals in the tree of life than they are to plants. And a couple of the things that make them really different are that they produce spores, which are very tiny propagules. And importantly, from the materials point of view, they are made up of hyphae. So hyphae are essentially long threads. And one of the key things is they're microscopic. So hyphae are in the order of 10 micrometers in diameter. So if we envisage this as a hypha, that's 500 times this straw, the actual size of a hypha. Hyphae grow at the tip and in effect indefinitely extend. Hyphae can branch, and they can also join up in anastomose. So eventually those hyphae growing in a substrate, whether that's soil or decaying wood, have the capacity to indefinitely extend and form a three-dimensional network. But because they're microscopic, we can't see them. What we see is the sporing bodies, like a mushroom or a bracket fungus, that are produced by this massive hyphae. Now, in terms of feeding, one of the other unique things about fungi is there's no digestive system. There's nothing internal like in an animal, and there's no plumbing like there is in a plant that moves nutrients up and down. So fungi, in effect, excrete enzymes out into their food. So to put it colloquially, they slobber over their food. So if there's some decaying wood there, the fungus is pumping out enzymes, breaking that down, and then absorbing the simple materials that it's broken down. And these fungi, being very fine, can penetrate into the finest little cracks in the soil to pull out nutrients, and they can get inside wood to decay it. In terms of the sporing body, we're all familiar with mushrooms and so on. Another type of sporing body is the bracket fungus. And one of the amazing things is that this is a bracket fungus, it's coming off a tree, that it's rotting. This is an aggregation of those very fine microscopic threads, the hyphae, and this is amazingly tough. So that's just incredibly fine threads all bound together to form, in this case, quite a persistent bracket fungus. Now these can get quite large. This is one of the biggest ones that we have in our collection here. So those incredibly fine threads that are 10 micrometers in diameter are all aggregated together to form a structure that's quite strong. This is actually quite light as well. And then the spores here are produced on the undersurface of that bracket fungus. So in terms of that feeding, fungi are feeding in quite a lot of different ways. So they're breaking down wood, and I have a wooden table here. Think how hard wood is. If you add water and a fungus to wood, that wood is completely decayed. So a huge log in the forest, several metres across, will decay down over many decades just to nothing. So fungi are fantastic recyclers in ecosystems, taking the carbon, nitrogen out of wood and litter, leaves, all sorts of organic material, feathers, fur, etc., and recycling those nutrients as insects, invertebrates and so on eat the fungi. Another really important thing that fungi do is form partnerships. So many trees and plants have a partnership with fungi. So in the soil, in effect, if we could blow away all of the soil particles and blow it up, so these threads of wool are about 1 millimetre in diameter, so this is about 100 times magnified, the soil would be absolutely full of lots and lots of different kinds of fungi connected to plants, rotting down wood and so on in an incredible network. But it's invisible. So one of the things I love about this project is that it's actually making fungi visible in a really interesting way, because if you walk through the forest or your garden, most people are only noticing the fungi when they see the fruiting bodies like the mushrooms or the toadstools and so on. So in terms of the material side of it, those fine threads that make up either the mycelium, which is the aggregation of hyphae in the soil, or the sporing body, which is the mushroom or the bracket fungus, these come in quite a lot of different varieties. What's happened with materials construction is that people have tended to go for the fungi that are already cultivated. And these are fungi such as oyster mushrooms, reishi, and so on, that are cultivated for food and or medicinal properties, particularly from Chinese traditional medicine. So these are fungi that over millennia people have worked out how to grow on organic waste, whether that's straw or pieces of wood and so on. And so there's information already about how to cultivate them. And these are the fungi that have been taken over into materials construction. But I think one of the really interesting things from a mycologist's point of view is that when we look inside a fungus, so this is a drawing of the inside of a fungus with all the different kinds of hyphae that are in there, you'll notice that there are hyphae that are intertwining between other hyphae. These are called binding hyphae. So there's actually quite a lot of different things happening. You know, there are probably several million fungi in the world, of which we only know maybe 5 or 10%, and they're forming their hyphae in lots of different ways. They're feeding in lots of different ways. And so for the materials side of things, we've only really trapped out a couple of different sorts of fungi at the moment, which have promise for that. But there's an incredible array of fungi out there that have great potential. And I guess that kind of comes to the kind of research we do here at the Royal Botanic Gardens Victoria. So I'm in a reference collection, a fungarium, which we have tens of thousands of specimens of fungi. And our role here is fundamentally to describe and document that biodiversity of fungi, to try and put names on them, to try and understand how to identify them, to catalogue them and so on. And then really that's the underpinning, the language, I guess, for all sorts of different applications in industry and medicine. Fungi are great sources of bioactive compounds like antibiotics and so on. And so it's quite exciting now to see another kind of frontier opening up with the materials construction side, where perhaps a fungus that we discover in a rainforest somewhere might be put together in a slightly different way, might have different digestive capacities on different kinds of organic substrate. And so I think there's a really interesting research now to take these kind of prototypes and then explore all the different kinds of amazing ways that we could incorporate fungi. So I'll leave it there, and really happy to come back towards the end and answer questions.
Awesome. Yeah, great. Thank you, Tom. It's super interesting. I love passion for and dedication to fungi. It's something that we all need to learn more about, and it's really fantastic to hear. And hopefully we can circle back with some more interesting discussion in a bit. So now, yeah, we're going to pass on to Nancy from Studio Edwards, and she's going to outline where this all started from. And so, yeah, over to you, Nancy.
Thanks, Alex. Hi, guys, I'm Nancy. So I suppose to begin with, this is Mooshi, but to start with, we were set a brief from Melbourne Design Week in 2019. They had a brief for the Design Waste Challenge, and that theme was waste. And I suppose we were asked to choose a waste-related problem and show maybe how our design ideas could help solve it. So for us, it was quite important. I think there was a lot of conversation around the Yarra and the waterways at the time. So we were kind of thinking about, is there a way we could clean the water, and could it be something that also fosters habitat and nature and interaction in that way. So we started kind of prototyping this thing that we now call Mooshi. Funnily enough, while we were doing this competition, we also met Daniel, who's from Swinburne University, who you'll hear speak later. And I think at the time we were sort of rivals in a way, presenting both our very different schemes. But I think it's a really, really nice kind of full circle to be working together to prototype this. Has been really, really, really special, I think. So I suppose, yeah, our response was this floating wetland for the Yarra made of organic waste. So it kind of addressed waste in two ways. We wanted to create something that would, I suppose, be made from waste, and then could it address the waste in the water. So the idea for Mooshi was that it would do, two things. One being, as I mentioned, kind of fostering this nature, and the other side of it being that it would maybe collect waste as well. So we had all these crazy ideas, and obviously we were thinking, it should be made from mushrooms and organic waste. So so this is sort of the kind of prototyping phase for us. Sorry, next slide, please. So you can see in this, it was this idea of this 500 mil triangular module, and the idea would be that it would form kind of tessellations. So once you made one, you could kind of link them together and create these two almost floating wetlands that would sort of sit alongside each other in almost a V shape, and then connecting the two would be this idea of this like net that might collect rubbish. I suppose we wanted to design something that collected rubbish maybe in a non-conventional way, and it was below the surface of the water rather than collecting above. And obviously, we're all really aware of the water pollution issues and just urban density and things like that. But water pollution in particular. So next slide, please. So I guess, we started prototyping with mycelium. And when I mean we started prototyping, we were essentially working in the back of our workshop in our studio. So, it wasn't probably the right setting or the right conditions to be doing this in. But it was we were just trying to get our hands on some reishi and see if we could actually grow the thing, before we went too far with this concept. But that kind of, I think, was maybe the turning point for us, where we started to think that if we wanted to create a prototype of this product or this idea, that we would have to maybe talk to some technical experts, not ourselves. I basically knocked myself out when we were doing this, because you had to sanitize everything. So we'd created this mold, and we had also these plastic containers where we just wanted to see how long it would take to grow, which waste materials worked better with it. I think we were using coffee beans here from our local cafe for the organic waste that we've shown in this image, and making it dampened and moist. But to begin with, you had to sanitize everything. So we were sanitizing with like vaporizing alcohol, and I was breathing it in. We hadn't aerated the space, and made myself very, very sick that day. Couldn't drive. Yeah, felt very out of it. But anyway, I think for us that was like a really exciting part as well of this project, because we I suppose wanted to see it grow, but maybe made us realize we needed to take it to another level. And here we're seeing like a sectional view. So the idea was that you would have the mycelium forming the base structure of it, and then there would be a portion of that would be filled with soil, so you could plant plants and foster this growth of the root system through the water. And the ambition with it was that maybe those roots would then be clearing the waterways as well, of reducing maybe some of the algae in the water. But obviously this is very conceptual for us, so then we weren't aware of how much of that soil versus mycelium to make it float. And then this, I suppose we were looking at what kind of plants did we want to plant in Mooshi, and what kind of birds are we wanting to attract? So, you know, things like the yellow thornbill maybe, or the swamp hen, and just this idea that there would be like a biodiversity to it. So there would be nature and yeah, I suppose like animals interacting with it. That would be the ambition overall. Next slide, please. Thank you. So, you know, with the diagram, this is sort of what I was touching on before. Can those plant roots maybe start to aid in reducing algae? Can they cycle through some nitrogen maybe? And yeah, that was the sort of idea and the thinking behind it. And yeah, and then as I was mentioning earlier, you know, could this be a trap for river surface litter? So not thinking about, you know, obviously the things that are at low level, but kind of taking the Bandalong River trap and wanting to understand, you know, obviously I think in 2009 to 2010, this took 2.7 tonnes of litter was generated through, I think, the 4,000 litter traps that we have in Victoria. But they are very costly, you know, they cost $50,000 to $100,000, and they're not, you know, aesthetically pleasing in a sense. And I suppose because the Yarra is such a place for recreational like activity, it would be really nice to be interacting with something that is also, you know, nature, and maybe does that job as well. So this is sort of what we were speaking about earlier. And, you know, can these two have like a kind of netting system that captures that litter, and then, you know, over time it just gets collected similarly to the Bandalongs as they get, you know, collected and cleared out every now and then. Next slide, please. And so that, I suppose, is like a sectional view of the ideas we were having. So part of the net would also sit slightly above. You know, we were also wary and cautious that if it was too low down, we would start catching fish and things like that. And that's, you know, definitely not what we were wanting to do. Next slide, please. And so, yes, I guess it kind of left us with this idea of like, we'd love to beautify the river edge and softscape it and, you know, make the waterway more attractive, but we certainly didn't have the knowledge to do it, as you saw with our our modular experiment in the studio. So it was about, you know, speaking to some technical experts, and I suppose we started having some conversations very early on with Arup. So over to you, Alex. You basically picked it up from there.
Yeah, thanks. Thanks, Nancy. Yeah, at this point, Nancy and came to Arup to see what we could do. You know, Arup is a firm, you know, independent firm of designers, engineers, architects, planners, and we work across, you know, a whole range of different areas of the built environment. But I guess more importantly, where we were able to help is that we have a research arm called Arup University, which looks to, you know, foster foresight and research, develop kind of technical skills and learning, and further insight into really interesting sort of topics that, you know, require investment back into our own research ideas, and that's where we were able to pick up the further development of this prototype. So when we got it, we were able to have a kind of step back moment and kind of think, what next, really. Being technical group, we started to ask a lot of questions. We started to kind of critique, you know, what the actual function of it was. You know, questions like, would it float? If you go back a slide, sorry. Kind of, would it float? Is it strong? You know, how do these modules join together? What kind of plants are involved with it? Where do you buy the material itself? You know, what happens when you put this mycelium structure in water? What happens then? You know, and then, yeah, what is the purpose of what we're trying to achieve here? And at that point, you know, there was a whole raft of questions that were really left kind of unanswered at this point. And so we really wanted to focus, I guess, on what we thought was an achievable purpose for the development. So we go to the next. And at this point, we recognized that one of the main challenges was how to connect it and how to maintain the structural integrity of something. And we, through a bit more research, realized that including the litter trapping function was going to be a challenge that we were trying to run before we could realistically. So we refined that a bit and really tried to focus on, creating this organic material, utilizing organic waste with the mycelium substrate, providing that habitat for wildlife, and providing a function to clean water, to remove the nasty chemicals from the water. So at that point, we kind of shifted the purpose of what we were trying to achieve. I think it's been quite beneficial. So from that point, as good as engineers, we started to do some desktop research. When reviewing this in 2009, there was very limited information that we could find on the structural properties of mycelium. Being an organic material, it's very hard to get a consistent data source, or there's lots of different substrates that you can choose, different species of mycelium. It's all a new product, so it's very difficult to understand how it would function in a real life scenario. Some of the research that we got was that by weight it is stronger than concrete, albeit it's very light. It's somewhat inactive when it's heated. It becomes non-porous as well, which was an interesting element thinking about the floating aspect of it. And then this is the point in which we started to engage further with Swinburne University. And through that, they uncovered something to us that was quite interesting around when the mycelium grows, if there is other cellulose material such as timber, the mycelium binds with it and somewhat forms a glue. And this was a really interesting aspect, and you can see on the right there that kind of wooden piece stuck in the mycelium structure that we wanted to explore further and realize was a kind of a key aspect of the material properties that would form the basis of how we would go about doing this. So from that point, we started to really refine the previous prototype that Studio Edwards had created to create more of this floating wetland piece that would facilitate the plant, the growth of the plants, but then also there was some sort of function that could tie these pieces together. So that's where you can see that we've got this timber dowel that we were anticipating would form, the structural element between the mycelium pieces. From that, we realized that there was this big lack of understanding around how strong is the mycelium when you have this like this, and what are the loadings, the wind loadings, when you have it in a river or a waterway. So we went away and developed a couple of different testing procedures that would be interesting to understand before we could realistically progress to the next stage. From that point, we realized that we also needed a partner, another project partner, and this is where Royal Botanic Gardens have stepped in, and they've been now providing us advice and guidance on the floating wetland structure. They have a series of floating wetlands that exist already. They're very much a proven technology to help facilitate cleaning of water. And so you can see on the left the picture of the floating wetlands when they were installed. And then, on the right, that's the same floating wetlands, albeit a number of years later, fully developed. So they're currently functioning in the Botanic Gardens, and this is where we started that relationship and have been growing that since there. So now, from doing this kind of desktop research and sort of pulling in the different stakeholders that would need it, Arup essentially provided the facilitation of from a concept, and then facilitating it into like, how do we actually build this? What do we actually need to do it? And that's where we really engaged Swinburne University from this point. And so now I'd like to hand over back to Daniel, who will run through Swinburne's role and how they took this very much concept and made it great.
Thanks, Alex. No, I really appreciate everyone coming here today, and I think you can hear a little bit of progress in the background as I'm speaking. However, yeah, here I am in the container within Brunswick East where we incubated the mycelium modules, or MUSHI. However, I'm going to pass over to a video which shows a bit of the background behind Swinburne's involvement with mycelium over the last few years with Kun Hui Chen, who has prepared a video that we'll play. I hope. Lachlan, take it away.
Morning, everyone. My name is Chun Hui Chen. I'm a lecturer at the architecture program at the Swinburne University of Technology. Today I will present to you some of the mycelium research we have done at Swinburne. I aim to show you not only some background research that forms the basis of the manufacturing of this current mycelium wetland and at the Botanic Gardens, but also want to show you some wider possibilities and potentials of this wonderful mycelium composite material. So the research of the mycelium composite at Swinburne University was started in 2018. It started with an annual 2-week intensive design studio called the ER Global Summer School. In this video, we seek to exploit this environmental benefit of this mycelium composite and explore the design opportunities that are unique to this material. Furthermore, we are also interested in using digital design and digital fabrication to unlock the design potential of the mycelium. In this workshop, our participants come from various design backgrounds, including architecture, landscape architecture, industrial design, and engineering. The work that I'm showing today in this presentation are the outcomes of this workshop done by this enthusiastic and hardworking participant on this video. So in this video, we first introduce students to the material in a very scientific way. We bring them to Swinburne Biolab, supported with Dr. Rebecca Alfred's support from the Biolab. Students were able to understand the scientific aspects of mycelium and also examine and look at this material under the microscope, really understand the fibrous structures and how it is. And next, students were taught how to sterilize substrate material and inoculate mycelium growth by themselves in the growing bag. Here are some of their growing. And from the material, physical material, we then jump to digital tools, and we design some bioscaffolds that allows the mycelium mixture to be filled in within the structure in order to gain the shape that we want. And then we use laser cutting tools and other CNC fabrication techniques such as CNC to fabricate our mold and construct it. Once it's constructed, the mycelium mixture will infill into this bioscaffold. Here's a picture, a close-up picture. You can see that this is at its very early stage. Only the white part has a little bit of mycelium in it. The rest are substrate. And then it will go through a period of incubation with constant temperature and humidity control. Mycelium will start colonizing the substrate within the bioscaffold. Here's a picture. It will start turning white and colonize all the substrate within the mold. And once it's grown, then we design the scaffold in a way that it could be just strip off easily and also reuse. So here's a picture on the very left hand side. That's the mycelium fully grown within the scaffold, and then remove it. And that's the outcome. And you can see the molds are still intact. We could use it again. And once it's finished, the molds removed, then the model will go through a drying process. It could be air dry, or you could use an oven to speed up the process. The idea is to get rid of the moisture content and kill the mycelium. Here are some of the shapes that we create. So it's the chitin that within the mycelium that makes it very, very strong. And we also explore the possibility of including joint, including accuracy in the model, because once we grow components, we were thinking perhaps they can be smaller construction elements that make up a larger structure. So again, here's a summary page. That's the process. Students will put in the mixture within the mold, which is fabricated and informed by our digital design process. It's a process. Once it's filled, we'll put it in the incubator for the mycelium to grow and colonize within the scaffold. And then we will dry it, and that's how we gain our structure. So after gaining some initial knowledge on the mycelium, students starting to look into their own interests and various aspects. For example, different substrate. So in 2018, Wenxin was looking at using coffee ground, the waste of coffee ground recovered from a local cafe as the substrate. So we went through the process of sterilizing it in the lab, and that's a comparison of the sawdust space growing back and the coffee ground growing back. So it is possible, and it will let mycelium grow, colonize it. However, the moisture content needs to be very well controlled, because the grind is very fine, and it's easier for it to absorb too much moisture, which will slow down the growth. And also, because it's fine elements, the particles, the structural stability needs to be further tested. And in this case, Ruby was examining growing a coffin for people using mycelium, and she did it by using, and she also explored using different material such as jute as the bioscaffold, which can be colonized by the mycelium itself and becomes part of the structure, so there's no mold removal needed. So here's some of the progress. And the model was filling when it's soft, it was hung, but then once it finished growing, when the mycelium hardens, you can flip it upside down and it would be structurally stable. So that's a quite interesting experiment there. So this is another idea from Gordon and Lily, who are landscape architecture students. So they were particularly interested in the aspect of oyster mushroom and how oyster mushroom can help recover some of the contaminated soil that's contaminated by petroleum. So here's some of the process how mycelium could break down the petroleum and recover the land and allow other species to grow. So they did some tests themselves as well, mixing petrol from the petrol station, and they mix it with yellow oyster mushroom, and then put them under the microscope to examine the growth, and the test was quite successful. And from there, taking this idea, they start imagining what the design could be, taking a piece of contaminated land and then divide it up and hopefully design this mycelium path. Once it's colonized, it will create this mat, and it will slowly allow others species to come back. So these are very speculative, but at the same time, it is very interesting thoughts that should be, could be, and should be further experiment in more details. And in this case, Leslie and Crystal were very interested in the acoustic quality of this mycelium material. They did some comparison between the mycelium panel and the acoustic panel called EcoPanel. And here are some of the results. So they developed a strategy that uses surface treatment to help with sound diffusion, etc. So surface treatment becomes their main aspects of exploration. Here are some of the results of the panels. So with the help of digital design and fabrication, we were able to create all different types of surface patterning within this mycelium panel. And students started to imagine what it could be. Perhaps it was an acoustic wall or meeting pot that's modularized, or combination with mycelium and other materials as interior linings. And finally, we also started looking into how to combine the manufacturing process of the complex mycelium models that we saw earlier with structural optimization process. This is called BESTL, bidirectional structural topological evolution. It's developed by Professor Mike Shea at RMIT Structural Lab. So in this process, we've given supporting locations and load conditions. The algorithm will start removing unnecessary material and add on extra material to where it's necessary. And through this process, it will finally generate structurally efficient model, outcome. So students use this method. Imagine it could be a mycelium pavilion with the organic structure. And we also tested the possibility of growing it accurately, growing this complex digital model accurately with mycelium. So we tested with some 3D printing and matching it with the AR.
Thank you for everyone who is attending today during their lunch break, I assume. So back to me in the mycelium incubator in Brunswick East. So I'm an architectural engineer from Swinburne University, architectural engineering lecturer there, And basically, a lot of the research that I do is about encouraging the use of construction materials that are low waste or zero waste. We've got a company called Curvecrete that operates out of this factory that does zero waste, beautifully curved concrete panels using robotic technology. But here we're focusing in on mycelium, which is a biomaterial, and mushi, who is made up of all sorts of different biomaterials as well. So I'm going to take you through a little bit of the journey that we went on in order to actually come up with this physical prototype. So next slide, please. So there's 4 key stages. The submerging, or hopefully floating, structure, fabricate, and incubate. And I'll take you through those now. Next slide. Thank you. So submerge. So we basically submerged a series of mycelium samples. So you can see 4 mycelium samples in the center of the screen there. And each one of them is actually coated with a different coating to experiment with what sort of growth patterns we got relative to the water level. So if we go to the next slide, the one on your left, I believe, hopefully, was charred, so it was burnt on the outside. The next one, second from the left, is a linseed oil, and the third one, a hard wax. The one on the right, I believe, is natural. So the growth doesn't stop, even though these samples are really dried out above the surface, but below the surface when they're submerged, there's no fruiting bodies that you can see there. So that was one of the observations that we found, and we hope with the one that we've deployed in Royal Botanic Gardens that we'll see hopefully some fruiting bodies above the water surface. So a key challenge for this was to solve some of the structural challenge was one of the key ones. So basically, mycelium we think is quite structurally good relative to its weight, but when we actually test it, it's a counterintuitive material. So so this one, I think Kia is helping us in the Swinburne Structural Lab, setting up the apparatus, and the small pins. If we go to the next slide, I thought they would have maintained the strength, but we had to fabricate a new rig just to take the load that the mycelium would actually transpose to the connection apparatus. So if we go to the next slide, and here's an angry engineer. Sorry, Lachlan, do you mind muting just quickly, mate? I'll just get a little bit of feedback there. But so I'm not usually this angry, but I'm looking at the steel that is deflected there, the mushroom beach steel in this case. It's a tiny little bit of steel, but on the right of the screen you can see the solution to that is to use these huge eye rings that can wrap around those timber structures. So what you really see here is a timber dowel that's embedded within the mycelium matrix to have a look at what sort of failure mechanisms happen around that connection. So we go to the next slide. So this is the failure mode 1. It's where it's a combined sort of how you would explain concrete failing, like a compression, like punching failure on the top of that dowel as it interfaces with the mycelium, but also a tearing sort of tensile-based failure mechanism around that region. If we go to the next slide. And something really interesting happened was that the second failure mode was actually on the top and it burst out. So it ripped apart. Next slide, please. So this is a second structural type 2 test. This is a little bit more similar to the in situ style a test that we're doing. So it's a symmetrical test, pulling these rods away from one another. If we go to the next slide, so the failure mechanism again here was very similar to the structural mode 1. So next slide. Looks like we're going to run out of time pretty quickly, so I'll try to keep these bits punchy. So we found that the mycelium structure by itself wasn't going to meet the structural requirements that we needed, so we needed to think differently along the lines of composite materials. And we thought back to one of the structural examples here where we had a timber lattice within the mycelium. There's a lot of surface area there that actually bonded to that timber really well. Next. And we began to experiment with different structural configurations of how we could use timber as the main structural component, where the mycelium would just make up the rest of the volume. Next, please. So we created these timber triangular lattice panels that were CNC milled, and we created voids within the timber where we thought the least stress would be experienced by the timber in order to create more surface area so that the mycelium could bond better with that timber. So here's the product of the prototype with 3 timber elements that interlock, and then the top and bottom components there that you see what make up the mold of the to shape the mycelium. And so moving on to fabricate, so the series of tests that we did on how to build these, but basically timber structure was CNC milled, and then interlocked, and the mycelium glue would hold that together. The mold was siliconed together, and then we tried to pack it. Next slide. Tried to pack the first mold, and it burst, or the silicon burst. So we fixed that with some steel bracketing. It's a lot heavier than we thought, even though it floats. And then we set up the incubation chamber that I'm in here in now, and lots of mycelium arrived. Here's the packing party, if you like, of us packing all of the mycelium-rich soil within the molds and positioning the structure. We were able to get some glass bottles as well, just from our non-alcoholic gin distillery in the factory as well. And you see Chen's quite happy with the result there. So we left them there to grow out within about a week, transported them to Swinburne to dry out and then hatch. Next slide, please. And then they went for a road trip from Swinburne all the way through the city to the Royal Botanic Gardens, where they were launched, and now they float in their new habitat. So what we're trying to test now is looking at the durability versus the biodegradability, so how long they're actually going to last, and what sort of reactions we get from the material itself and how it degrades. And also, we'll get to the biodiversity side as well, but just looking at the materials itself, we're testing 3 different surface treatments that we're going to test over the space of about 3 months or so with constant monitoring. So on the left, we have the burnt coating, the hard wax in the middle, and the natural naked finish on the right. And then next slide. And then we're testing 3 different types of timber as well. So we've got a standard CD grade structural ply on the left, a low formaldehyde content poplar pine in the middle, and a soy laminate poplar pine on the right as well. So we're going to see what the the differences are, and we are looking for some assistance with this during this time that it's at Royal Botanic Gardens over the next 3 months. So we are opening up for everyone to engage with this exhibit by observing what sort of biodiverse animals or birds, etc., that interact with this. See if you can spot what happens with the lovable named Mushi prototypes, and each one of the modules, Robbo, Popo, and Steve. So I'll open it up to Alex to wrap up with closing remarks and the Q&A session.
Yeah, thank you, Dan. I think there's quite a lot of information in what you've kind of gone through and what the research behind what Swinburne University have done to get to this point. So, yeah, hopefully people that are still online can engage in some questions, and we can flesh out some of those more details, through answering. But what else can you do from here? Mushi is live in the gardens. It will be there for the next 3 months, and when we'll remove it, and through that period, we'll be monitoring different aspects, and streaming the prototype. So you can see there on the star, that's where you can go and visit it, and I really encourage everyone to get out there. And it's a beautiful spot to go and spend an afternoon as well, and just look at it and think about the future of biomaterials. So if you want to go to the Botanic Gardens, recommend looking out for this sign. On there, you'll also find a QR code in which you can scan to learn more about it. There'll be an element of that citizen science where you can engage and help us with the monitoring and the live stream. And there's also an opportunity to follow us on Instagram at Mushi the Mycelium, all with underscores. Great. So I guess thank you everyone for listening. Big thank you to Melbourne Design Week and Open House Melbourne for helping us facilitate this. We now have an opportunity to engage in some Q&A as well. So yeah, I think maybe next slide. Yeah, okay. So I guess I'll just address the first question here from Nicola around, is Mushi heavy or light? This has been a real concern of us throughout the development. Will it float? And as you can see, it is light enough to float, and it is about half the density of water. So half of it is submerged in the water itself. The next question is from Philip. Was Mushi form tested that the triangle is the best performance for plants floating, etc.? I think. Daniel, do you want to elaborate on this point at all?
I think the started out as a triangle. We think probably the ideal geometric form for this sort of thing is kind of like a boat underneath. But geometrically at the top, you want to look at how you can tessellate it so that you can have lots of these for the purpose of getting those roots to expose themselves to the water. And I'm sort of addressing another question there, but basically we're looking for the most amount of surface area that we can cover and a safe habitat for birds to interact with and that sort of thing. So we don't really want sharp edges and that sort of thing that could harm wildlife. So we rounded out the chamfered edges, and we didn't want it to deteriorate either. So that would reduce the risk of the corners sort of breaking off. So it's a hybrid between this hexagonal and triangle. So that's how it ended up.
Yeah, great. Yeah, I think it's interesting. Yeah, the shaving of the edges. The mycelium doesn't actually grow very well at a corner. The pocket ends up being not very well established. So that was another consideration about chamfering the edges there. There's a question here from Christina about, is there much linkage on micromediation / biofiltration for air quality? And if so, do we know which species most suited, and if there is any impact of spores on indoor spaces? This question I'm going to pass on to Tom if he thinks he's up for it. I think this is a very, very technical question. So yeah, pass to you, Tom.
Great. Look, it is a good question, and I think really, and for some of your other questions, Christina, I think there's a lot of science still to be done around this. One of the things to keep in mind with fungi is that mycelium is not producing spores. It's only the what I call the sporing body, sometimes called a fruiting body, that produces spores. So if you're just growing a big mass of mycelium, most of the time there's no spore production from that. But you could imagine a large mycelial mass grown in some way, because there's lots of little spaces in between, that it could form quite an interesting filtration material. And I think there's a lot of things out there, like your question about if you grow oyster mushrooms on organic waste, are the sort of toxins transferred into the mushroom? They're just all great science questions that can be tested by setting up replicated trials and measuring. And what I really love about this mushy thing is just the amount of, all this testing of tensile strength and all these other things that we're really starting to get information out. Whereas I think kind of 10 or 20 years ago, there was a bit of a vibe that mushrooms could do anything, but we hadn't really translated that into the science and the technology around it. So great questions, and hopefully somewhere there'd be a research group that's picking that up and doing the necessary trials.
Yeah, thanks, Tom. I think did you touch on just then, Tom, about does it come back to life when introduced to water?
Not really, but that's a question I had for you guys when you put it into the water.
Yeah.
And you said, well, it's still alive. I mean, sometimes when you're making, say, interior paneling out of mycelium, or packaging material, which is now very commercially viable, that would be baked or treated in such a way as that it would be dead. But if it's not treated at a particularly high temperature or really completely dried out, it is still alive, and so it will keep growing. And so these floating islands may actually start to put out little sporing bodies off the side of them. And that's something that could be controlled in the manufacturing process, depending on the temperature and the time of drying. But these definitely have the capacity to put out sporing bodies, which would be fantastic if they do.
Yeah, I think on the previous slide that Daniel presented, our tests that we did, even though we thought that they were dead, they still produce that fruiting or sporing body as well. So I guess it's an unknown from here. This research is definitely a world first for floating mycelium wetlands, and the path forward is still unknown. So I might pass to Nancy here and address Polly's question around, do the roots still come out of the bottom?
Yeah. Hi, Polly. Yeah, so I think you may have seen in the video that we showed at the very start, that Alex showed, we actually drilled holes through the mycelium structure so that would kind of enable obviously water to access the plants and then roots to start to grow through and into the water. So yeah, the intent is still there.
Yeah, exactly. So the function of the floating wetland works better when the roots are in the water. Daniel, I might pass to you now, just to comment around, and kind of linking to the previous question about, is Mushi still alive when you plant within it? And maybe you could just make a comment around what it was like before when it was alive and when it's not alive, just the kind of material properties and handling that.
Yeah, absolutely. Just to be aware, you might hear like a nail gun in the background. I'm okay. The really interesting thing for us when we experimented with this one is it's the biggest volume of mycelium that we've ever made. So we don't know yet actually what's going to happen in the depths of the structure. So even though we dried it out for 3 or 4 days in around about 35-degree climate or thereabouts, we dried it out as much as we could within those days, within the time that we had. But we think, and we also hope, that some of the mycelium is still alive inside, so that the fruiting bodies might emerge. But the whole point of drying it out was to get a stiffer mycelium matrix. So when the mycelium is still growing, it's still very spongy before it really becomes rigid. But then when it dies, after we dry it out, it becomes quite stiff. You put it back in the water and it gets a little bit spongy again, but not quite as much. And it still stays together quite well. So there's a couple of things that you touched on there, Alex, but I may have forgotten 1 or 2 points. But I think the interesting thing is, if you are really interested in looking and observing this at the Royal Botanic Gardens, have a look at the one that is burnt, because that one, which is really fascinating, grew the most amount of fruiting bodies when we tested it previously. So even though we've dried it out and we've burnt it, it might still emerge and create some really beautiful fruiting bodies on the surface.
Yeah, the fruiting bodies and the kind of is it alive, is it dead, is really an interesting concept that yeah, I don't think we know the answer to that, and stay tuned for the next few months to find out. There's a couple.
It's like the Schrodinger's cat of mushrooms.
Yeah,
we'll see.
We will see. We will see. There's a couple of kind of technical questions here that I might have to pass to. One around the Austerum mushrooms being able to be consumed after micromediation on a petroleum site. And that's a really interesting comment, which I'm not too sure about the answer of that. And then the second one around Asparagus oryzae. Tom.
Yeah. So to pick up on that, as I mentioned before, with the toxins potentially from the organic material moving to Pleurotus, not really sure. With Aspergillus oryzae, that's actually a really interesting question, because if we're thinking about materials construction, so Aspergillus is a fungus that used a lot in fermented and other Asian food, one of which is and if it's not the same Aspergillus, there are quite a few different fungi involved in that. So over thousands of years, these have been developed into for food use. But thinking of something like tempeh, which is it's like a soybean matrix, a soybean food with the fungal matrix holding it together. In effect, that's like a material, isn't it? It's just a rather soft material. So really, from that food, for maybe for thousands of years, people have been making a fungal material, but something that's edible. So, and this again shows the incredible properties of fungi in terms of being able to produce all sorts of different enzymes and so on to help break down the food, convert different substances in the soybeans to more palatable material. But yeah, it's very interesting to look elsewhere now. Most of the inspiration, I think, for these mycelial composites has come from the kind of cultivated mushrooms like the reishi that's been used here. But yeah, there's just, like I said, there's millions of fungi out there, most of which haven't been discovered yet. So all sorts of incredible possibilities in the future, I think.
Yeah, very, very interesting. I didn't quite know the connection then between tempeh and fungi, to be honest. I eat tempeh quite a bit, so I'll look at it slightly differently now. So we're probably, reaching the end of our time allocation here. So I might just see if there's kind of two more questions here, one from Rosemary and one from Philip that we might just answer quickly. I might answer the one from Philip quickly. So what type of plants are most suitable for Mushi? We tried to make a balance here between plants that would facilitate the kind of cleaning of the water through the wetlands. So you can see the plants on the outside of that aerial shot that's on screen. On screen. But the smaller plants are used to clean the water, and they're like a juncus variety. And then the central plants are more about promoting a natural habitat. I can't quite remember what the Latin name for that is, but there's more information that can be found on Botanic Gardens' website as well. And then there's a last one about the research into mycelia for construction of coffins, which I might just pass to Daniel to maybe comment on briefly.
Thanks, Alex. So that project I'm not super familiar with, but Kanoi Chen can certainly give you some insight on that, and if you get in touch with him. However, rather than making mycelium enclosures for dead people, we will be looking at enclosures for people that are still alive, and looking at building some potential larger structures that you could inhabit and experience at a much larger scale. So we're looking at opportunities to produce something, and we're very open to fresh ideas there. And yeah, maybe it's something curvy. We don't know, but Jen Kanoi has given some provocative images around what could be built, which is pretty exciting. So if there's anyone interested in getting involved with mycelium, do reach out to us, because at Swinburne and at Arup, Siri Edwards, Royal Botanic Gardens, we're all really interested to see what else is possible with mycelium, especially on the large scale. So yeah, thank you very much.
Yeah, great. Well, I think we'll probably wrap that up there. I just want to say, a big thank you to Nancy from Siri Edwards and Ben Edwards as well. Dan and Chen from Tom Royal Botanic Gardens for presenting today and spending the time and working through this prototype together. I also really want to do a shout out to the rest of the Arup staff that have really helped pick this along. Alessandro, Lachlan, Jess and Kim Rawlings. They've been really helpful for us. So yeah, thanks very much for everyone for listening as well. Thanks for engaging with some really interesting questions. Please get in touch with us if you want to learn more. I really encourage you all to get to the gardens as well, and check out Mushi in person. It's really beautiful there. And yeah, thank you again.